Okay, so let's go ahead and get started. So the exams should be graded by Thursday, so I'll be turning those back then. But today what we're going to do is we're going to continue talking about a circuit element that we haven't spent as much time on so far, and then we're going to move into magnetism. So to this point, when we've been doing circuit analysis, we've been primarily dealing with resistors and talking about what the current is through a resistor and what the voltage is across a resistor. But another circuit element that we could talk about, and we've talked about it kind of in passing but not in full detail, is the capacitor. And so what a capacitor does is it separates charge into the positive side and the negative side. So some plus Q over here, some minus Q over here. And effectively what this does is it stores energy. And so what a capacitor does in a circuit in an electronic system is very similar to what a spring would do in a mechanical system, in the sense that a spring can store potential energy, and so can a capacitor, just in a slightly different sense. And so when we talk about capacitors, we're interested in what the electric potential is across this capacitor. So what is the V that's across here? We could write this by saying that V is going to be equal to Q divided by C, where Q is the amount of charge that you have on the capacitor, and C is the capacitance of the system. Now we know that our V we can measure in volts, Q is a unit of Coulomb, C is a unit of what is called farad. Typically these are very small numbers, and so you'll talk about things like microfarads or nanofarads, but we give this the letter F to denote that it's a farad. And so, like I said, we could also talk about what the potential energy is stored in the capacitor, and there's a couple of different ways we can write this coming from this equation. And so that's to say that the potential energy stored in this capacitor is going to be equal to 1/2 Q squared divided by C, or you could also analogously write this as 1/2 C V squared. Okay? So when we're looking at capacitors in circuits, you can follow exactly the same types of rules that we followed when we were doing circuit analysis with resistors. Only now, instead of saying, for instance, if I have a resistor, what is the electric potential difference across this resistor, we would say that this would be some V is equal to IR. Now, if we have a circuit and we want to do some circuit analysis with capacitors, we say that the electric potential difference across the capacitor is going to be this Q divided by C. Okay, so we have a couple of practice problems, and then we're going to do some circuit analysis with these, and then over the course of the class today, we'll be moving into magnetism. Okay, so any questions about these equations that I laid out here? Okay. So let's take a look at our first question of the day. This one says a capacitor of 0.75 microfarads is charged to a voltage of 16 volts. What is the magnitude of the charge on each plate of the capacitor? So go ahead and talk about this one. Okay, so let's go ahead and talk about this one. I think it was a pretty straightforward calculation. And so what I tell you here is that you have some capacitor with capacitance of 0.75 microfarads, and this is charged up to a voltage of 16 volts. And what we want to do is we want to determine what the charge is that you have on that capacitor given these two pieces of information. And so what we can do is we can go to this equation that tells us what the electric potential difference is across a capacitor given the charge on it and what the capacitance is. And we can rearrange this in order to solve for what the charge is. And so what that says is the charge on some capacitor Q is going to be equal to V times C. Now, a way that you can kind of remember what this equation looks like is if anybody still has cable, I doubt anybody really does, but used to be this home shopping network called QVC. And so Q is equal to VC. Okay, so we know what the voltage is, we know what the capacitance is. This voltage was 16 volts, so this is 16 times 0.75 microfarads, but this is really a 3/4, and so this is going to be 16 times 3/4 times 10 to the -6. So this is going to cancel here. You get a 12 times 10 to the -6, or 1.2 times 10 to the -5 coulombs. Q is equal to 12 times 10 to the -5 coulombs. Okay, and then that's the answer. That should be answer choice B. Okay, any questions about that? Nice, easy one to start out with. Okay, so the next one says, the sketch shows a simplified representation of a parallel plate capacitor. The plates have a capacitance of 175 microfarads and a potential difference between them of 2240 volts. Find the charge stored on the plates of the capacitor and the energy stored in the capacitor. So go ahead and talk about that one. And for whatever reason, this slide doesn't work. Does there have animations on this? Let's see. No, there are no animations. Scoring options. No, that's... Okay, so let's go ahead and talk about this one. This one really just kind of builds off of the last question, just adds another piece to it. So in this question, we're told, again, what the capacitance of the system is and what the potential difference is across this. And what we're meant to find is what the charge is and what the potential energy is for the system. And so what we see here is that we're really using exactly the same equation that we used last time in order to determine the charge. But now additionally we need to determine what the potential energy is, and so we can use this equation right here in order to find what the charge is, and then we can use this equation to find what the potential energy is, and when we do that we end up finding that this is answer choice A. This is 0.39 coulombs and 439 joules. Okay, any questions about this one? All right, so moving on. Okay, now this one, it's going to take a little while, but this follows the same types of rules that we were using before when we were trying to find the equivalent resistance of a system, but this one's, when you find equivalent capacitance, it's just slightly different. And so let me remind you of this table that I drew. So when we look at finding either the equivalent resistance or the equivalent capacitance, we need to think about whether we're adding the circuit elements in series or if we're adding them in parallel. So for resistors, what we ended up finding was in series, when we add these together, we say that this is going to be Req is equal to R1 plus R2 plus ... In parallel, this says that 1 over Req is equal to 1 over R1 plus 1 over R2 plus ... Now, for capacitors, we end up seeing that this is just the reverse. So when we add these in series, this says that this is going to be 1 over Ceq is equal to 1 over C1 plus 1 over C2. And in parallel, Ceq is equal to C1 plus C2 plus ... Okay, so based off of the rules that I've laid out here and our knowledge of how to collapse these systems when we want to find some equivalent capacitance in this case, go ahead and try to solve this one, and then we'll talk about it afterwards. It might take a little while. Okay, so let's go ahead and talk about this one. So walking around, I think almost everybody had the beginning. It was kind of the middle where people had a little bit of difficulty. But I think if you draw this step by step as you're collapsing these, it makes a lot more sense. And so, like I said, the first step almost everybody had right, and that had to do with collapsing this in parallel and these three in parallel. So when I do that, what I end up seeing, this is going to be our 12. This becomes a 120. This 50 is still here. So we have our 50. We have our 12. This is going to be our 60. Now this one over here is going to become a 60 because I have 30 plus 20 plus 10. So we have a 60 here. And so, like I said, almost everybody was able to get here. Now, this is where people started having problems because it's like, well, what can I add in parallel? What can I add in series? Well, it turns out the only things that I can add together at this point are these two, because these ones are going to be in series. Now, the rule for adding these in series goes that 1 over the equivalent capacitance is going to be equal to 1 over C1 plus 1 over C2. So that says 1 over 60 plus 1 over 60. Inverse is going to be, this is going to be 2 over 60. So when you invert that, this gives you 30. So let's draw this again. So we have our 12. Here's our 120. This is still our diagonal 50. This is also 12. This is, now what I have over here is this 30. So the next thing we can do is we can notice that this one and this one are now in parallel with each other. And so the next part that we can draw is adding those together, and because these are in parallel, they just directly add. So we have capacitance of 80 here. So this is going to be 12. This is 120. This is now 80. This is our second 12. Okay. So we're moving right along here, and at this point it becomes a lot easier to see what we need to do. So we have this 120 plus 80. These are going to add in series, and so this says 1 over 120 plus 1 over 80. Inverse is what we're looking for. We have to find a common denominator. So 12 and 8 have a common multiplicative factor, or it's not a common multiplicative factor, but 24 is divisible both by 12 and 80. So we want to get this to be a 240. So in order to do that, what we do is multiply this by 2 over 2. So this is going to be 2 over 240, plus this gets multiplied by 3 over 3. So this is going to be 3 over 240. And so when we add this together, we get 5 over 240. When we invert this, we get 48. Okay. So now that we have this, I'm running out of room here, so I'm going to come back and just erase the one that we had here. So now what we're going to have is this is going to be our 12. First 12, second 12. This is going to be 48 now. And we can add these together in parallel. So when we add these together in parallel, we're going to get 60, and we're almost there. So this says this is going to be 12. This is 60. We add these together in series. This is 1 over 12 plus 1 over 60. Common denominator here is 60. If we multiply the first term by 5 over 5, this says that this is going to be 5 over 60 plus 1 over 60 gives us 6 over 60. We invert this, and then we get our final answer, which is just going to be 10. Okay, so the numbers worked out pretty cleanly here. Any questions about this one? Okay. So you just have to kind of do it step by step, and you have to be careful. I think the most common thing that I saw when people made mistakes, it was because you didn't show all of the steps. If you show all of the steps, the logic flows pretty naturally, and you can see what you can and can't add together. Okay, so let's move on to the next one. So the next one is just doing a little bit of circuit analysis with these, and finding what the charges are on these capacitors, and what the voltage is across them, and what the energy is stored on them. So kind of going back to some of the calculations we had done a little bit earlier. Okay, so go ahead and talk about this one. So, for the first circuit that we have with the capacitors in series, we want to find what the charge is on each of the capacitors first. And so the way that we can do this is to add these two in series to find the equivalent capacitance. So we have this equivalent capacitance now, CEQ, where this is going to be equal to 1 over 12 plus 1 over 60 inverted, which is going to be just 10, right? So what we end up seeing is that because this equivalent capacitance is going to be 10, is this in microfarads? Yeah, 10 microfarads. Because this equivalent capacitance is going to be 10, the charge on the equivalent capacitor is going to be 100 microcoulombs, because the charge Q is equal to V times C. So we know what the equivalent capacitance is, we know what the voltage is. And because these two capacitors are going to be in series with one another, the charge on each one is going to be the same as the charge on the other. So the charge on these, so I can call this Q1, is going to be equal to Q2, which is going to be equal to the charge that I had on the equivalent capacitor. So this is going to be the 100 microcoulombs. This was our epsilon. So if we want to do the same thing with our parallel circuit, we kind of run into some problems here, because what I'd have to do is I have to say that if I collapse these in parallel, then that I could find what the total charge is on that, but that charge is split between these two. So the sum of the charges on these is going to be equal to the charge on the equivalent capacitor. So what's actually a little bit easier here is, instead of using these equivalent capacitance rules, is to just do two loops here. So if I do two loops here, what I ended up seeing is that the charge, so let's call this Q1 and call this Q2. Q1 over C1 is going to be equal to epsilon, and Q2 over C2 is going to be equal to epsilon. So this says Q1 is going to be epsilon times C1, which is going to be 10 times 12, so this is going to be 120 microcoulombs, and Q2 is going to be equal to epsilon times C2, which is going to be equal to 60 times 10, so this is going to be 600 microcoulombs, okay? All right, so now the next thing that we want to do is to find the voltage across each one of these. And in order to find the voltage across these, we have the charge. And so what we can do is we can say that the charge divided by the capacitance is going to be the voltage across this. And so we know that each one of these has 100 microcoulombs. This has a capacitance of 12 microfarads, and so this is going to be 100 divided by 12. This one has a capacitance of 60 microfarads, and so this is going to be, this is V is equal to this. This is going to be V is going to be equal to 100 over 60. Okay. Now we actually already know what the capacitance, or sorry, what the voltage is across this one and this one, because we actually used it already to find what the charge was. And so the voltage across this capacitor C1 and C2 over here is just going to be the 10 volts that we have for the battery. Okay. Now the last thing that we need to do is we need to find what the energy is stored in each one of the capacitors. And now that we have the voltage and we have the charge, this is pretty straightforward, because we have the equation for finding what the potential energy is when we have either the voltage or the charge. And so when we look at that, what we end up seeing is for the system on the left, we have energies of 416 joules and 16 joules, and for the system on the right, we have energies of 600 and 3,000 joules. Okay. Any questions about that? Yeah.
Where did you get the 10 volts for the parallel one?
10 volts for the parallel one. It's because of the because really what is this? This is the V1. This is the voltage across this one. Call this V1. Call this V2. Right. But because of the loop rule, the change in electric potential around the closed loop has to be 0. So increase by 10, decrease by some unknown amount is equal to 0. And so that means that whatever this decrease in electric potential is here, it needs to be the same as the increase, and that increase was 10 volts. Yeah. Okay? Other questions? All right, so we have one more capacitor question, and then we might have some time to do some magnetism at the end. And if we don't get to that, we'll definitely be doing that on Thursday. So go ahead and look at this slide that I didn't change, because I changed the slide on my laptop and not over here. So we have this circuit here. What we'd like to do is to find what the charge is on C1, what the voltage is across C1, the voltage across C2, and the charge on C2 and C3. So go ahead and take a look at this one and spend some time trying to solve it. Okay? Okay, so let's go ahead and talk about this one. So we had this, this circuit where the capacitance of C1 is going to be equal to 30 microfarads. The voltage is going to be 12 volts. C2 is equal to 20 microfarads, and C3 is going to be equal to 40 microfarads. So the first thing that it asks us to find here is to find the charge on C1. And so in order to do that, what we can do is we can find what the equivalent capacitance is for the system. And then when we find the equivalent capacitance, the charge on the equivalent capacitor is going to be equal to the charge on the capacitor C1. So in order to find the equivalent capacitance, the first thing that we can do is we can add C2 and C3 together in parallel. And so since this is 20 microfarads, this is 40 microfarads, this is going to give me some equivalent capacitance for that portion of 60 microfarads. This is still our 30 microfarads. This is going to be our 12. And so the next thing that we can do is to collapse these two in series. This tells me that 1 over 30 plus 1 over 60 is going to be equal to 1 over CEQ. So this is going to be 2 over 60. So we have 3 over 60 inverted, which is going to be equal to 20 microfarads. So what that tells us at the end of the day is that the equivalent capacitance is going to be 20 microfarads. We have a voltage of 12 volts, and so in order to find what the charge is on the equivalent capacitor, we end up saying that this is going to be Q is equal to V times C, which is going to be 12 times 20, which gives us 240 microcoulombs. Okay? So now what we can do, now that we know that this is the charge on the equivalent capacitor, that's going to be the same as the charge on C1. So we know that Q1 is going to be equal to this 240. Okay. Now the next thing that we can do is we can find what the voltage is on V1. Or sorry, the voltage is across C1, because we can say that that voltage, V1, is going to be equal to the charge on the capacitor, Q1, divided by C1. And so what we can do is we can plug in these values, and so we have 240 microcoulombs divided by the capacitance, which is going to be 30 microfarads. And so when we do this, we end up seeing that this is going to be 8 volts. Now, the next thing that it asks us is to find what the voltage is across C2. And so the voltage across C2 we can find by doing some loop that goes around the outside. So when we do this loop, we end up finding that epsilon minus V1 minus V2 is equal to 0. We know epsilon is 12, V1 is 8, and so in order for this to be equal to 0, V2 is going to be equal to 4 volts. Okay? So now that we have V2, we can find what the charge is on C2, because V2 is going to be equal to Q2 over C2, or Q2 is going to be equal to V2 times C2. And so this is going to be 4 volts times the capacitance here, which is 20 microfarads. So this is 20 microfarads. And so this is going to give us 80. This is going to give us 80 microcoulombs. Did I do that right? Yeah, this looks good. This looks good. Okay. Now, the last thing that we can do is we can find what the charge is on our C3, because, again, we can say that Q3 is going to be equal to V3 times C3. And so we know that V3 is ultimately going to be the same as V2, because we could do some loop around here. So V2 minus V3 is equal to 0, and so V2 is equal to V3. And so when we plug this in, we see that this is going to be 4 volts times 40 microfarads, which is going to be equal to 160 microcoulombs. Okay? Now, the interesting thing here we find is that when we add Q2 to Q3, so I have Q2 is 80 microcoulombs, and Q3, which is 160 microcoulombs. When we add these together, we get 240 microcoulombs, which is the same as what we found for Q1, right? So Q1 was the 240. So what this says is that Q1 is going to be equal to Q2 plus Q3. And in some sense, that establishes a junction rule for charges, right? So if I had this Q1 over here and the Q2 and Q3, the Q1 is going to be equal to the Q2 plus Q3. So in some sense, junctions behave the same way in capacitors as they do with resistors when we're talking about current splitting. Now we have the charge that's splitting here. Okay. Any questions about this one? Okay. So we have 8 minutes to start a new topic. I think we're just going to, I'm going to let you guys go early today, and we'll start magnetism on Thursday.